So thank you everybody for joining us for the last joint colloquium of the semester. Just a heads up also to people on Zoom, we're considering removing the hybrid option for the coming winter semester, so you can send all your complaints to me. Okay, so to introduce our speaker.
Hi, good afternoon, everyone. It's my pleasure to introduce Tim Davies, who is visiting from the University of Cardiff today and tomorrow. Tomorrow he will be mostly up at MPIA. So Tim received his PhD in 2011 from the University of Oxford, and he then moved to an ESO fellowship in Garching, where he stayed for 3 years, and this is where we also got to know each other and overlapped for a while. Then Tim got the prestigious Ernest Rutherford Fellowship and took that for a year to the University of Hertfordshire before moving to the University of Cardiff as a lecturer first and senior lecturer, and now you're a reader there. So he has been at Cardiff for 10 years, and he is one of the leading experts in ISM studies in extragalactic environments. He has been very much involved, one of the leaders within the Atlas 3D project. He is a co-PI of KILOGAS, which I think is also, he's going to be talking about that today, and Wisdom. And one of the main aspects that he is known for is, for example, he has been pioneering the work on determining supermassive black hole masses from molecular gas kinematics. I'm very excited that you accepted our invitation, that you came here, and we're looking forward to your talk. Thank you.
Is it on now? Now it's on. There we go. Sorry about that. I'll be telling you a little bit about the work that I've been doing using the coldest gas in the interstellar medium. I'm popping it a little bit, move it away. There we go. That should be better. In order to probe the potential of galaxies and how they form and evolve, especially around black holes, but not entirely. So a lot of the work that I'm going to talk to you about concentrates on the centers of galaxies. So galaxy centers are one of the most dynamic and interesting parts of galaxies because they're where all of the physical processes that we care about when we think about the formation and evolution of those systems really matters, and it all is interplaying with one another all the time. So the centers of galaxies are where the majority of the star formation happens. If you think that gas is distributed in an exponential disk, that means most of the gas is in the middle. And so you've got a lot of star formation happening in that environment, and that's being mixed up with a very deep potential well there. You've got a lot of mass concentrated within the bulge of your galaxy, and that gives you all sorts of interesting dynamical effects like shear, etc., that are interesting and important down in those environments. You've got your supermassive black hole that lies in the center, and that affects you both dynamically and through any energy output that does as it accretes. You have gas inflow and accretion from the surrounding environment, from the spiral arms, from the bars in galaxies down onto the center of that system that are bringing material in, potentially fueling that supermassive black hole. And so those gas flows all have to move through this region if they want to reach down and head down onto that black hole. And once that black hole's fueled, then it's going to output some energy, be that in jets or winds, that have to all tunnel through the centers of the galaxies in order to impact the larger galactic system. So they may create outflows, they may not, it just depends what's going on. And so all of these processes are all happening at the same time in this same spatial region of a kiloparsec or so in the centers of galaxies. And so if we want to understand how these all work and how they interface and impact the evolution of the system, galactic centers are a great place to study. So I'm going to be concentrating on 3 main questions as part of this talk. So the first one is about black holes. So why do black holes seem to care or know at all about the galaxy that they live in? And then how about living in this deep potential well? What does that do to change the structure of the interstellar medium, change the star formation that goes on? How does that interplay work? And then I'm going to talk to you a little bit about the future, about how we push these sorts of studies, not just at the centers, but the disks of galaxies as well, across the galaxy population in large statistical samples with our new survey called KILOGAS. So that will just be a little section at the end showing you first results. see how that goes. So in this talk, I'm really probing these questions using the coldest gas in galaxies, the molecular material. So as I'm sure you're probably all aware, but it's bears saying again, this is the material that's observed in emission from molecular species. So this is gas typically down at 10, 20 Kelvin, where the majority of the gas is in the form of H2, but H2 is very hard to trace observationally, and so we typically use tracer molecules. So species that are less common, but are more observable, like carbon monoxide. So one of the most abundant molecules in the universe outside of H2, and readily available in atmospheric windows to be observed from the ground. And the great thing about this gas that I'm going to use a lot here is that it's a great dynamical tracer. It's such a cold gas that its own thermal pressure is not very important in holding it up. It mostly moves like a tracer particle within the potential of the galaxy. There are ways and places where it might not, but for the majority of the time, it shows you how the gas is moving because of the potential. And that's really, really useful. So we'll start off by talking about black holes then. So the question is, why should a black hole care about the galaxy that it's in? And you may think that this is a silly question, right? Of course they care about each other. There's a big black hole and it's living in a galaxy and it should know about each other. But actually, that doesn't make a lot of sense. The black hole itself, its sphere of influence, is only a few parsecs in size. But a galaxy is many kiloparsecs in size, right? So gravitationally, the galaxy knows nothing about the black hole that lives in its middle. But yet somehow the properties of the galaxy and its black hole are linked. That's weird. We want to work out why that happens. So why do we think that these relationships between black holes and galaxy properties exist? Well, we think that feedback is important. So we have a loop where you end up, take a galaxy, it has some gas in it. That gas is forming stars, and some tiny fraction of it will make its way into the center of the galaxy and trickle down onto the black hole where it accretes. Black holes are incredible engines for extracting energy. You get nearly half the rest mass energy out when you accrete material into the black hole as it falls in gravitationally. So you've got a lot of energy available, and if you can couple that energy from jets or winds to the surrounding material, you can blow gas out of galaxies. And so you can imagine a self-regulated feedback loop where gas falls onto the galaxy, forms some stars, flows into the middle, triggers the AGN, blows out some gas, and so you end up with a self-regulating structure where galaxies and their black holes grow in lockstep over time. And that's our typical picture, and it's how we think we go from galaxies like our spiral type systems like the Milky Way that live on the blue cloud. Something moves them rapidly from there onto the red sequence. We think that the energy from AGN is a great way of doing that. There's also many other reasons we think that active black holes or active galactic nuclei are important. So, for instance, the galaxy stellar mass to halo mass relationship doesn't look anything like it does in the simulations unless you put black hole feedback in. There are many reasons we think that black holes should care about their galaxies. But the question is, if this is true, what I've just told you, then galaxies that don't currently have any gas, that live up here, that are red and dead, quenched type systems, they should have bigger black holes than galaxies of the same stellar mass who haven't been quenched by that black hole. That black hole hasn't done a work in that galaxy yet, hasn't done the work in order to remove the ISM, so it should have a small black hole. And it would be nice to see that signature in the observed black hole galaxy population picture in order to prove that this picture is really what's going on. And so people have looked for this, and this is one great example from O'Connell and Marr here. So here you see almost all the black hole mass measurements that have been made at the time dynamically. So this is the black hole mass on the y-axis, and the velocity dispersion, so how the random motions of the stars near the center of the galaxy that's effectively tracing the galaxy mass. You can think of this as a galaxy mass axis. So you can see as the galaxy gets larger, so the black hole mass gets larger. And you see the color of the points here denotes what type of galaxy they are. So whether they're a galaxy that's actively forming stars, then they'll be blue here. If you are a quenched system, like an early type galaxy, elliptical or lenticular, then you're red. Or if you're a brightest cluster galaxy that live at the center of a deep potential well of a cluster, then you'll be green here. And you can see that the red and the green points, their best fit black hole mass velocity dispersion relation is in red, and the blue points, their best fit relation is in blue. So you might think, happy days, we found this relationship that we're thinking of, right? Black holes of quenched galaxies are larger at fixed galaxy mass. But you've got to be wary, because if you look at the symbol shape in this plot, almost all the spiral galaxies have their black holes measured through, they are triangular points or circles. Because what's happened there is they've measured the black hole mass using either the kinematics of masers, so effectively microwave lasers in the accretion disk that light up when the disk is seen edge on, and we can track the motion of those masers as they rotate, get excellent black hole masses, or from motion of the ionized gas in the centers of those galaxies. Almost all of the quenched system are stars on here. They've been measured using the kinematics of the stars as they rotate around the black hole there. So when you see relationships like this, where different traces have been used and you've got different normalizations, you've got to worry. Is this systematics or is this real? We want it to be real, but do we know it's real yet? We would really like to find a way to measure the black hole masses in these galaxies using the same tracer in both types of populations, so that we could be sure it's not a systematic tracer difference that we're tracing, and really is the galaxy evolution difference that we see. And so I've already sort of spoiled the punchline of what I think we could use here. So what we want is something that's dynamically cold, so we can really use it to trace out the potential. It's present right the way to the middle of the galaxies, and it's observable at high angular resolution, so we can zoom in around that black hole. I told you that the sphere of influence of a black hole, so the region where it gravitationally influences the stars, is only a few parsecs in size. For a typical Milky Way mass black hole, it can reach up to maybe 30 parsecs in a very massive black hole, but that's still very small, so we need high angular resolution in order to do that. The really exciting thing that I've been involved in pioneering here is using molecular gas for this. So you may say, well, Tim, that's all well and good in your spiral galaxies that have a lot of molecular gas, like this one on the right-hand side, this is pause data taken from APA, Ava Shinner's group, I think. Maybe not. Anyway, it's a spiral galaxy. That's all of them have molecular gas, brilliant. But your early type galaxies, you said they're quenched. Well, it turns out that actually 22% of early type galaxies actually have molecular gas reservoirs in their centers. They aren't forming many stars from that gas, but it's there. And that gas is essentially there independent of the other galaxy properties. It seems a lot of it is either brought in through mergers or it's cooling from the halo. It's not forming many stars for reasons we'll go into later, but it's there and we can use it to trace out the potential. It's very low velocity dispersion, it's dynamically cold, and with ALMA we can get very, very high angular resolutions indeed. 10 milliarc seconds is fairly standard. We can go higher if we want to, and so we can really zoom in around black holes and use this gas to trace out. So to do this, we started a survey called WISDOM. Everybody knows in astronomy you have to have an acronym for it to be a real project. So ours is Millimetre Wave Interferometric Survey of Dark Object Masses. It's all first letters if you ignore that millimetre bit, so I think that's pretty good. And so the aim is really to pioneer using this technique to measure the supermassive black hole masses, both of spirals and of early type galaxies, using the same technique. Try and pin down, is there really a difference in the black hole mass relation between those, or is it all systematic between others? So we have about 45 galaxies observed now, from dwarf galaxies right the way up to massive ellipticals. We've got resolution from about half a parsec out to about 40 parsec in our more distant, more massive sources. So we're really pushing down right into the region around those supermassive black holes. And we've got high velocity. You can easily see the motions that are going. So how does it all work? So here's an example for you. So this galaxy is NGC 383. It is a massive group center elliptical galaxy. You can just about see, if you squint, right down there in the middle of the bulge. It goes a little bit darker than you'd expect from just if you were just extrapolating the light profile by eye. If you zoom in with the Hubble Space Telescope, you see there's this little dust disk in here. This whole thing is only about 500 parsecs in radius. And so this is really a small molecular disk, although it has about 1 billion solar masses of gas in that disk. So this might be physically small, but it contains as much gas as the Milky Way in molecules. The blue color here is Chandra. And you can see that there's a jet-type structure coming out here. And indeed, this is 3C31, a massive radio galaxy. So we know there's a big black hole in the center of this system. And this dusty disk here very likely hosts molecules, that we can use to zoom in on. So there are old observations taken in 2010 with the Plateau de Boer interferometer with 2 arcsecond resolution. And we can see here there's definitely molecular gas associated with that disk. But in 2010, that was about the best we could do. But with ALMA now, we can do oh so much better than this. So we went out to observe this system with ALMA. So instead of 2 arcseconds, we went to 0.2 arcseconds, or 0.1 arcseconds. And this is what the disk looks like with ALMA. See, an absolutely stunning disk. If I showed you this without this label, you might say this is a protoplanetary disk. They look so very similar. Disks are disks all the way down. You can see there's lots of beautiful structure in here, some spiral arm type structures. There's a concentration of gas in the middle. Very nice indeed. This was work by a PhD student of mine, Eve North, some years ago now. And actually, you can do much better than this. 0.1 arcseconds with ALMA is relatively easy. And we now have observations of this system at 0.03, so 30 milliarcseconds. This is down at 10 parsecs in this system, 66 megaparsecs away. And so here, you can see this disk breaks up even more into, you see those spiral arms that we saw before come out even better. This disk in the center now starts to break up into little clumps. So you can really see the 10 parsec structure of the molecular gas in this galaxy center a long way away from us in this massive elliptical. Paper was just accepted a few days. Watch out for it on the archive this week or next week. So the really nice thing with this is the kinematics are beautiful. So this is the velocity field of the disk. So blue shifted, red shifted in the standard way. And you can see it's just beautiful rotation. It looks like a model, which is lovely. And you can also see, if you know what you're looking at, you see in the center here, you see how the red and the blue pinch together? That tells you there's high rotation, hundreds of kilometers a second, right the way down to the center of the object. That already tells you there's some large mass sat down there in the center. But we don't just do this by eye. What we can do is we can look at this even better. But what we can do is we can pop down a pseudo slit on our galaxy and extract out a position velocity diagram, so how the gas moves as a function of radius along the major axis of this system. And this is what we get at our 3040 parsec resolution. You see the flat rotation curve of the system at large radius out of the kiloparsec here. And then as you come in towards the center, rather than dropping to 0, as you would expect the gas to do if there was no black hole, it peaks up as the gas goes faster and faster and faster as it rotates around the supermassive black hole, the center of this object. You can see the Keplerian rise as you get towards the center of the object. We can use this, or in fact, we use the whole velocity cube, but we can use this to model this. Now, as a sneak peek, if you go to our new, even higher angular resolution data, this becomes even more stark, right? You really see this. This is a zoomed-in view, of course, but you really see this Keplerian rise right the way up here to 700 kilometers a second away from the systemic. So this is gas rotating about 10,000 Schwarzschild radii from the black hole. Yes. We detect that relatively easily with ALMA a couple of hours. So we don't just, one could just, overlay a Keplerian curve and actually measure the black hole fairly easily from this. That isn't what one should do full 3D kinematic models. So we use the KINEMES tool, which I created. So this is a observation simulation tool, forward modeling, Bayesian tool in order to model your kinematics. So if that is something you would like to do for any of your sources, be they high redshift disk, protoplanetary disk, anything like that, then this could be a great tool for you. So come chat to me afterwards or check out the website, kinemes.space. And what we can do is do a full fit to that. We get it that this is a 3 billion solar mass black hole down here in the center of this galaxy here. So a nice big meaty black hole in that system. But we don't just observe massive galaxies. We also observe things right down in the dwarf regime. This is what Nadine was involved in with me. So this is NGC 404, a dwarf galaxy. It's about 3 megaparsecs away from us. It's called Mirach's ghost because it's near the bright star Mirach, and so it appears like a ghostly apparition behind it if you stare long enough around that bright star. And it's a beautiful little dwarf galaxy, a few 10 to the 9 in stellar mass. And you can see, if you zoom in with HST, there's this dust disk around it. So we thought this is a great target to go after to try and study these sorts of things. There's a larger scale H1 disk that goes well off the screen here as well. This is probably accreted gas from a companion that's spiraling onto this dwarf elliptical as it goes. And so what we can do with ALMA is zoom in on this. This was the previous best image, 7 arcsecond resolution. The paper said high angular resolution observations. And then just a few years later, we go and blow this completely out of the water. With this map now is of the interstellar medium of this dwarf elliptical at half a parsec resolution. It's pretty impressive, I think, if I do say so. So each of these things here is an individual giant molecular cloud in this dwarf elliptical. So this one's about 30 parsecs in size, for instance. And you can see the beautiful structure that you've got here. You've got this one-armed spiral that goes into the center from this ring here that is actually projected out of the plane of the system. This is at a different inclination than the stuff in the middle. And then the stuff at the outskirts is warped again. So this is a whole dynamically relaxing system of gas spiraling into the center of the galaxy. And the black hole actually lives not here, but here, the center of this little disk, right down in the middle. We can kinematically model that, and we get a system that lives here. It's 10 to the 5.8 or something in black hole mass. So we can use this technique of using the molecular gas to measure black hole masses right the range of the M-sigma relationship. So here you see the points from McConnell and Marr in gray, and then NGC 404, this dwarf galaxy, and then the red auroral galaxies that we've used using this technique as of 2020. We've got more now that are coming out on the archive all the time. So we can really use this survey to make a nice difference in terms of the black hole sigma relationships and trying to see these offsets. You might say to me, okay, this is great. What about this thing you pitched me with about the difference between spirals and the early types? The answer is, watch this space. We don't have quite enough spirals yet that we're measuring. We're working on those. They're a little bit more complicated. They're a little bit more messy. And so those are all to come. The difference at the moment, if you take the masses of these, I haven't colored them by morphological type here, is at about the 2 sigma level. So we'll need a few more objects to just secure that, but watch this space. But it turns out when you go and do such a survey, observing these type of galaxies at unprecedented resolutions, you can detect some interesting and weird new trends that shed light on new areas. So we'd noticed as we were going through that ALMA, it doesn't just give you the line emission, but it also gives you continuum. And we detected millimeter continuum point sources at the center of each and every one of our galaxies. And we thought, well, this is just going to be dust around in the torus of the black hole. You know, this isn't going to be something super interesting, but you know, we'll just have an investigate of this at some point. These are unresolved on sort of 5-10 parsec scales in our data. But then we had a look and say, okay, well, what fluxes would we expect for these if this was just within the torus of the black hole, so around the central accreting region? And the fluxes we got were orders of magnitude above that. Okay, well, it's not that. So what about synchrotron? we've got jets in some of these sources, right? So we got the radio measurements, and we estimated how much millimeter flux we should expect, orders of magnitude above. Okay, well, what's left? Well, free emission. So maybe we've got star formation in the center, and we've got H2 regions, and the electrons in those H2 regions banging off each other, creating free emission. Again, orders of magnitude less than you would expect. It's not any of those things. What is it? Well, we thought to ourselves, this is something to do with the black hole. Let's see whether it correlates with the black hole mass. It does. So here, we've got the millimeter luminosity plotted against our dynamically measured black hole masses. The ones that are open on dynamical measurements, they are just estimators using the sigma relationship. You can see that there is a relationship here, p-value is 10 to the minus 10, between these millimeter fluxes and the mass of the black hole itself. That's now starting to get really interesting, right? There's 0.5 dex, so there's some significant scatter, but just by measuring this millimeter continuum point, which is really cheap and easy to get with ALMA, one could have a rough estimate of your black hole mass. That's pretty cool. We make it better. Can we try and understand the physics of what's going on? It turns out that if you include the X-ray luminosity coming from the central regions of these sources, that it gets even tighter again. So we're now at 0.3 dex, but the same scatter as the M sigma relationship. So our points again are the blue and the white here. Ignore the green ones for now. And so this is a plane here. There's a plane between the X-ray, the millimeter luminosities, and the black hole mass. And that rings bells because there's a similar relationship between the radio luminosity, the X-ray luminosity, and the black hole mass. This is called the fundamental plane of black hole accretion. I think it's a silly name because it's not fundamental, so why do we call it that? But that's what we call it. And so we call this one the millimeter fundamental plane of black hole accretion by analogy, even if you think the name's a little silly. And so what's the physics behind this? This is what we want to know. We've already said that this is not the same emission mechanism that is producing the millimeter photons as producing the radio photons. This is not the extrapolation of the jets. This is something else, but it correlates in the same way with the X-ray and the black hole mass. Something's going on. This is telling us something about accretion down in the cores of these systems. But what is the physics? Well, so one other point. These are all low luminosity AGN we have in WISDOM pretty much because they were selected to be a local galaxy sample where we could measure the black hole masses. They don't include a lot of bright AGN. There's a few, but not that many. But what we can do is we can take the bass sample of AGN. So these are selected in the hard X-ray. And so these are very highly accreting systems. We find that they fall on the same relationship, albeit with much more scatter. That's because their black hole masses are not measured dynamically, right? They are measured through relationships, and there's a serious correlation between how you measure the black hole and where you lie on this relationship. So we believe that they are still following this same relationship that we have. And that's very strange. It's very strange because these things are supposed to have entirely different central engines. So if you have a black hole, the typical model that you're probably thinking of when I talk about a black hole accretion disk is the top one. You have your black hole, you have a gap, and then you have a flat, flared accretion disk that's blowing a wind off it, and then outside of that you have a dusty torus, some geometrically thick donut-like structure of dusty clouds, which is around that material. In a low luminosity AGN, that is not what you get. Your accretion rates are lower, much lower, and so you can't sustain that structure. Instead, what you get is a disk at larger radii, and then it puffs up into a quasi-spherical, radiatively inaccretion to accretion flow, or RIAF or ADAF, advection-dominated accretion flow, where the material moves at subcaplarian velocities, slowly arcing into the black hole. It's optically fixed to its own radiation, and so it can't radiate away as much, and so your system is much less luminous than you would expect, given its accretion rate. And this is the sorts of systems that we think drive stronger radio jets. So our low luminosity systems should look like this in their centers, and high luminosity ones should look like that. And so if the centers are producing the same relationship between their millimeter and their radio, something is strange. And if we think about that classical accretion disk, the spectrum arising from that, from the torus and the accretion disk, you've got a big optical bump directly from the accretion disk. This is reprocessed into the X-ray and gamma rays. But as you go into the millimeter, the regime that we're looking at here, there's very, very little emission predicted at all from that picture. Just going to be any dust from within the torus. That's the only thing you should see there. It would be thermal dust continuation. Very low levels. Unless there's a jet, but then you're really only seeing the tail of that jet. So there's very little millimeter emission there. If you think about an ADAF, however, on the other hand, that's not true. What you have is you have self-absorbed synchrotron emission as the electrons spiral around the magnetic field lines within this big rugby ball-shaped plasma around the black hole. This creates optically thick synchrotron emission. It creates this bump here, and then that is Compton scattered up into the optical and into the X-ray, and then there's also a Bremsstrahlung component. And so here, you actually peak in the submillimeter. So we cannot reproduce what we see with torus emission. So instead we thought, well, let's try these ADAF models or REAF models to see, can they predict what we observe? The answer is, oh. On my screen, there's a gray bar behind this that overlays the data and shows that the model works. But you can't see that. So you're going to have to check Rufer et al. 2023 for all the details. Alaria Rufer was my postdoc working on this at the time. So ADAF models accurately predict the existence of this plane, which is fine for the low luminosity sources. We expect them to have ADAFs. But the high luminosity sources, we don't. But yet they follow the same relationship predicted by the same REAF model. So what's going on? Well, one option is potentially compact jets. If you have compact radio jets, they are also self-absorbed synchrotron emission. And so you can get a similar spectrum, but compact jet models we tried required a lot of fine-tuning to give us this relationship. You need to essentially be viewing all of them face on and with a certain range of energies, which seems unlikely, but maybe there's some parameter tweaking that could go on. So what we think is going on is that there is some radially inefficient part of normal accretion disks, a puffed up layer of REAF-type plasma around those accretion disks that are actually probing using this millimeter emission. So there's a lot of next steps here. We're working on stellar mass black holes. We showed that they follow this exact same relationship. It does seem to be an accretion process that we're really probing here. Variability is also important. So the NGC 1068, for instance, very well studied nearby AGN, you can study this same thing. It falls on the relationship, and you see variability on day timescales. So you know that this is coming from the plasma really down on light day timescales around the black hole. So we can probe this using the frequency dependence, etc. But this is all work in progress. So watch this space. But this millimeter fundamental plane is an interesting and exciting way to probe black holes, as well as the dynamical measurements that ALMA. So for the first part of the talk, I can't tell you why the galaxy cares, but I showed you hopefully that we're making a lot of progress on this. And millimeter continuum is really good. So I'm going to move on to the deep potential black hole now. So we know that the star formation efficiency, so how much gas is turned into stars in a given time within galaxies, is not constant. We already know from the galaxy that star formation is inefficient, but it's even more inefficient if you go to galaxies that have low star formation rates for their stellar masses. So very massive systems. You can see the color gradient as you go across this star formation rate stellar mass plane. These galaxies are very inefficient at turning the gas into stars. See the same thing down here. This is showing early type galaxies in red versus spirals in blue and black. You can see they're turning their gas into stars about 2 to 3 times less efficiently than their spiral galaxy cousins. And galaxy to galaxy, there's a lot of variation. So this is for using our wisdom data. We've got Muse observations here. And you can see that each galaxy follows its own Kennecock-Schmidt relationship. between the molecular gas surface densities and the H alpha star formation rate surface densities. So here, each galaxy is forming stars at a different rate from a given amount of gas. So some physical process must be mediating this. We wanted to look at what this is. So we wanted to see how the ISM is changing as we go from spirals right down into the pores of the gas disks in these early type galaxies. But with WISDOM, the great thing is we have molecular gas maps at 10, 20 parsec for a range of galaxies for free as part of our black hole mass measuring technique. What we started to notice is that they looked very different, even when you were putting them on the same spatial scale. So the gas in galaxies, in early type galaxies, this is the top row, these are all early type galaxies. And these are spiral galaxies observed at the same physical resolution at the bottom. And you can tell the difference by eye. You may think, well, spirals obviously have spirals, right? But we're looking at in a kiloparsec or so in these galaxies, right? Down here, down here. That's deep within the bulge anyway. The potential is quite spherical. Why should they really care about the fact that there's spiral arms in the stars at larger radius? Dynamical time's much, much shorter. They don't know anything about what's going on out there. But the gas seems to know about the galaxy that it lives in. So in the early types, the gas is very smooth, sometimes has these central holes. There aren't very many large, clumpy structures. There doesn't seem to be anything above about 30 parsecs. Everything, all of the molecular clouds are quite small. And there's low distances between those. The opposite in the spirals. So then that makes you think, well, what's going on? And one place you can look and see what's going on is simulations. So you've probably seen these plots before because they were done by Yindra Gensior during her PhD here. But Yindra did a numerical experiment where she looked at this. So she put idealized simulation of a galaxy. She put the same stellar mass, the same dark matter mass, the same gas disk in, and all she did was she changed the distribution of the stars. The top here, they're all in a disk. The bottom here, they're all in a massive bulge, 90% of the mass, very concentrated. You can see as you go from the top left, everything's very flocculent. There's lots of large structure. Down to the bottom, the central kiloparsec here, very smooth. It looks like the disks of our early type system. So as you concentrate that potential, everything gets smoother. Everything gets much more like the observations in our early type. So what we can do is we can study this, try and quantify this. And so we use these statistics the optical astronomers like to use, so Gini, asymmetry, smoothness. These are all ways of classifying the morphology of the disk by doing various morphological transformations on it. And we can measure these in the simulations and the observations. So here I'm combining the WISDOM data with the FANGS data that I'm sure you've all heard about hundreds of times, and with the simulations of Yindra, which are in the green. And we measure these things. So what we find is that there's strong correlations between all of these. So smoothness and Gini are essentially measuring the same thing, how smooth that disk is. Asymmetry is how asymmetric it is. And you can see that there's strong correlations between all of those, and the simulations follow very similar tracks. The data with some small offset. So gas disks that are very smooth are very symmetric and vice versa. And then we said, okay, well, we can use these and correlate them with galaxy properties. What you see if you do this, the ISM morphology correlates with things that trace the depth of your potential well in your galaxy. The stellar mass here, all the simulations of the same stellar mass, why they're all in the green there. You can see that the early type systems, the red, WISDOM galaxies here, all have very smooth, very symmetric disks and are high stellar mass. And the FANGS galaxies trace out a line here. Velocity dispersion, we have fewer galaxies, but you can see they basically follow the same trend. And then this is the stellar mass surface density within the central kiloparsec. That's our strongest correlation that we found with these morphology measures. So it seems that it cares about the potential well that it is. And one can just see this by eye. So here I've plotted the Gini versus this stellar mass surface density and just showed you the maps. So you can instantly see by eye this effect, right? They're much more blobby, less symmetric, more asymmetric than they are down here. So that's sort of really visual way of doing it. So we thought, well, okay, but what happens if it's not anything to do with the stellar density? Maybe it's to do with star formation, right? Spiral galaxies have lots of star formation, and so if you're blowing holes, the supernova, etc., maybe that's what's going on. Then you would expect to see a positive correlation between the surface density of the molecular gas, for instance, which should correlate with star formation, and these parameters. but you don't. You see a negative correlation. This is not due to star formation feedback. This is just a relationship between the stellar and the gas surface densities, no correlation there, and no strong correlation with the mass of gas in your galaxy other than the early type systems have low gas fractions. Go figure, that's what makes them early types. You don't see any correlation with the star formation rate, really, or the specific star formation rate other than early types are low by construction. You do see a small trend with star formation efficiency, but whether that's which way round the causative is there, it's not very strong. And so what could be going on here? What could be the physics underlying this? And one thing that's important is the stellar distribution. So if one thinks about the stability of the gas disk, you can use the Toomre stability parameter to quantify that. But it matters not just the stability of the gas disk, but also the stability of the stars. So the total of the system is effectively dependent on both of those. And so what we can do is plot the ratio of these to see which is dominant. What you see is that in almost all of our systems, especially the early type systems, they're incredibly dominated by the stellar stability. This is typified by the fact that in some of our massive early type galaxies, there is something like 7 times more stars within old stars within each molecular cloud than there is gas mass. So they're really dominated by the stellar component, and that matters a lot. If you're dominated by that mass component, then the deeper your potential well, the more shear you're going to experience. So we've shown through resolving the individual giant molecular clouds, as I'm sure Eric has told you about before, that what seems to matter, both in the simulations and the observations, is the shear and how that pulls clouds apart. If you imagine you're a cloud, you're orbiting around a galactic center, the tides there are going to pull that molecular cloud apart. So you have to be a very dense molecular cloud in order to survive in that environment. So here we've got a parameter space that shows this. This is the density of the cloud as a function of the velocity of dispersion of that cloud divided by its radius. It doesn't really matter, so effectively this is just the random motions divided by the length. If you lie up here, then your cloud is unbound. It doesn't stay together as a single entity, ever. If you lie in the disk of the Milky Way, and you follow Larson's relationships to molecular clouds, you should lie along this line here. But if you add shear into those relationships, and how the tides that are caused by shear pull apart those clouds, then as you increase the shear, so typified by the Orte parameter here, as you increase it, more and more of this parameter space becomes unbound. You cannot lie here and be bound. So only the dense cores can survive. So you rip apart all the big molecular clouds, turn them into little fluff. Unbound is moving around. And that's why these disks, we think, are much smoother in the center of the galaxies. And this very likely, at least in the simulations, it's definitely true. It's what's suppressing the star formation, because you've got much less mass in bound systems that can then go on to collapse from stars. So that's the conclusions from this part of the talk. How many minutes do I have? Then I'll just say very quickly a few words about the next steps that we're very excited to take KILOGAS collaboration. So our knowledge of the molecular ISM and how it impacts galaxy evolution is really shaped by these big statistical surveys, right? Things like cold gas really set our picture of what we expect for cold gas in the universe. But we don't really have the resolved equivalent of that yet. So what we'd like is large resolved surveys of galaxies, but not just galaxies that are typical spirals or starbursts, but things beyond the main sequence as well. And to really map out the star formation efficiency changes, we need to cover that full parameter space and observe both the fuel, this molecular gas, and the fire, the star formation that's happening. So we want to combine molecular gas observations and IFU observations on a large sample now of galaxies. The things like Edge Khalifa are the biggest thing that's been done before. So that's hundreds of galaxies. The data's not very deep because it's Karma. It's beautiful, and they've done a lot of brilliant work. But we can do much better than this now with the ALMA telescope. People have done this with ALMA a little bit. So ALMA Quest is the largest ALMA study so far. Combining these has 50 galaxies, and you can see here they've been mapping out these multi-parameter spaces between star formation, gas stars, etc. FANGS obviously has also been doing this with their beautiful CO maps. They've got 100 or so galaxies now, but their IFU sample is smaller and they're all above main sequence galaxies. So we want to push and do this better across the main sequence. And so that's what KILOGAS is for. So it's kiloparsec investigations of local objects, gas and star formation. And we always have to have acronyms. And what we do compared to the other competitor samples here is typified by this plot. This is our selection. So we've selected galaxies to be fully representative across the star formation rate, stellar mass, and size planes of galaxies. And this is compared with the ALMA and FANGS Muse samples that are shown in the pink and the blue here. And you can see we cover the main sequence in a much more statistical manner. So we can really use this to get at the physics across the galaxy population. We have 450 galaxies with ALMA and with IFU data from either MANGA or SAMI. So our resolution's about kiloparsec, and these are our 500 galaxies mapped across. And so we're really aiming to bring this sort of science into the large data era there across this huge number of galaxies. So we've got beautiful ALMA data. I'm going to whiz over this because I know I'm late for time. Beautiful ALMA data tracing out kinematics, spirals, all of this beautiful stuff. And we can compare that with the IFU data that gives us the star formation rates, metallicities, the stellar velocity dispersion. Really trace these across 450 galaxies in the local galaxy population. So some very quick first results here are, these are our molecular gas maps convolved down, reducing the resolution to match the IFU across the main sequence. And so you see already how small things get when they drop below the main sequence. So there's a key result there already. We detect a lot of systems on the main sequence, drop away when you go below. This is fully expected. These systems, when you see the star formation rate main sequence, you always must remember the things down here are almost all upper limits in their star formation rate. This is not a bimodal relationship. These things really go down to minus infinity at bottom. Star formation is very hard to measure when it's low. But we detect galaxies across the color magnitude diagram. So we have a lot of systems with a lot of gas right in the red sequence galaxy. So we can trace out with this sort of sample the full mass distribution of the local universe, for instance, because we have a representative sample that we can correct to be volume limited. And we can look at how molecular gas fractions move, etc. Work on speeding through, so because I know I'm late for time. Our galaxies, we can measure their sizes, so we get molecular gas reservoirs out to about 12 kiloparsecs in some cases. Typical is around 4 or 5. You can see that typically the gas is about the same size as the effective radius in galaxies on the main sequence, and drops when you go below or above. Lots of beautiful physics ongoing there that we're going to be able to probe with this set of data. I'm just going to whiz over now. Come after that. Here is our Kennigan-Schmidt relationship, so the relationship between star formation rate and gas mass, now with 1.3 million spaxels across 350 galaxies that we detected. Absolutely beautiful. Compared to things we've done before, and we can pull apart all of those variations that we saw before. Here's 10 examples of individual KILOGAS galaxies and the Kennigan-Schmidt relationship. These are the galaxies that they refer to, so you can look and see there's a lot going on here. The star formation efficiencies are changing a lot. This galaxy here has a low star formation efficiency everywhere, despite it being a blue spiral. This one is a messy merger. That's high. That's great. We think we understand why that is. But what's going on in different galaxies is really not clear. And so we can underpin what this physics is as we go forward. We can pull out relationships. So, for instance, this is how the Kennigan-Schmidt, their movement above and below this Kennigan-Schmidt relationship as a function of stellar mass. You can see that there's a clear trend here with more massive galaxies dropping below. This is the same plot from the ALMA survey with 50 galaxies, and you can see the power that having many more galaxies gives you. You wouldn't say that there's a relationship here, whereas here you know that there definitely is. That's the power of having much. We get the beautiful kinematics that we can treat in the same sort of way that I was talking about earlier in the talk, so we can have rotation curves for 400 galaxies, and see how they vary with stellar mass very clearly already. There's a lot going on here, Halley-Fisher relationships. And then there's all sorts of weird oddballs that come in a sample of this size. We've got big merging systems where you clearly see tidal bridges, inverted mass metallicity relationships. We've got molecular gas selected outflows. These things are really cool because normally we would go out and select an AGN or a starburst sample and then go look for how many have outflows. But here we can do the opposite. We can say, here's a grab bag of galaxies. How many have outflows from the molecular gas? Which is an entirely different experiment. There's so much science that can be done with KILOGAS. I wanted to just give you a sample of that excitement here. I will leave my conclusions.
So, questions?
Thanks for the great talk and beautiful data. It's really cool to see molecular gas being detected in quite a large fraction of early type galaxies, but still in the majority of them, we don't tend to detect it. So I was wondering, do we know if the gas-rich early type galaxies are representative of the early type galaxies as a whole?
Yes, this is something we looked at quite a lot in Atlas 3D, and indeed they seem to be. There doesn't seem to be any difference in the fast rotating early type galaxies between those that are detected and those that aren't. The only major difference we saw was that those that are slow rotators, so really are the dispersion dominated things you think of as classical ellipticals, which are only 10% of the population, it turns out, those don't typically have molecular gas. Everything else does. So that's what led us to believe that a lot of this material is brought in from outside, be it cooling from the halo, misaligned halos in a lot of cases, that or mergers. So we think that this is the first order, independent of the properties of the galaxy itself.
I'm not a student. Thanks for this fantastic talk. I was wondering, in the context of your second part where you talked about shear, right? And there is another elephant in the room that you have not touched, and that is bars and these very mostly radial flows with very high velocity towards the CMZ type structures that you also see in abundance, so central molecular ring-like structures in these galaxies that are clearly connected to the inflow from these bar. There is lots of shear. There is a huge increase of the velocity dispersion as these dust lanes hit the CMZ. And that is not captured in many of the simulations you've shown, yet it is a prominent feature and probably one of the dominant features explaining the star formation rate in its relation to the surface density. Can you comment on that?
Yeah, I think you're exactly right. Right, in our own Milky Way, right, we think that the CMZ goes through these cycles because of the bar where it has low and high. You know this is much better than I do. That's almost certainly important in some of these cases. A lot of the late type galaxies will have these big bars that can funnel material into those central zones. Even a lot of the early type galaxies, actually, a lot of the disks are sometimes all within the X2 orbits of that central bar. There, you don't have a lot of gas inflow anymore because it's gas exempt on the outside, and so not entirely clear that that's what's going on there, but certainly the stirring up that you can cause with the bars could be important, and is important to include in this sort of picture.
Thanks, Tim, for this beautiful talk. I had two questions. One very quick one. Like, do you include the mass of the cold gas into your dynamical model, and how much is it?
Yes, so we can include the mass of the cold gas. Typically, it's entirely not dominant. Typically, it's 3 orders of magnitude lower than the stellar mass in the same region, and so completely could be neglected. And so we normally do neglect it. In some cases, like in 404, we did include it, and it made a bit of a difference, and it went in a counterintuitive direction because it actually increased the black hole rather than decreased it.
Exactly. So that's pointing to my next question. If you now compare for galaxies that also have stellar mass, dynamical mass measurements for the black holes, do they always agree with your black hole masses from the dynamics of the cold gas?
Yes, so we have ALMA proposals exactly targeted at these sort of cross-check measurements. There are, I think, 3 published now, and they're pretty good agreement between them. There's small offsets of order a factor of 2 that we think are relatively easy to explain away given the errors. But certainly it doesn't seem like there's huge offsets in those 3 that we've managed to check so far. Typically, the good stellar targets are not the good molecular targets. Can be
So, a very, very quick last question. In your KILOGAS survey, these look like they're further away, but can you still measure black hole masses in those galaxies?
Yeah, so these ones are typically further away, certainly not with the observations we're taking in KILOGAS. Some of the ones that are the more close by ones, we could, if there are good targets, we could probably select out from there and go back to get higher resolution observations. The molecular gas outflows I showed, I've asked in ALMA for zoom-in observations of those in this current cycle. Maybe some of you reviewed the proposals, so we will see whether we got anything on that very soon.
Thanks for a very nice talk. I was wondering about the first part where you talked a lot about the y-axis of the black hole mass, or essentially galaxy dynamical mass, I guess. But what about the sigma e? Like, how can you measure that self-consistently for the star forming galaxy? Like, what are you actually, do you account for rotation?
Yes, so it would certainly be, yes, so that's certainly an issue in terms of the very star-forming systems. It can be very difficult to measure sigma. So you can use other things. You can use stellar mass relationship that's not as strong. You can use bulge mass relationships. So you try and photometrically deconvolve. So we can look at all of those proxies, and we should expect to see the same sort of trends in offsets as well. Probably not as clearly because it's not as tight a relationship. But yeah, it's a problem. And there are Muse programs that have been trying to. There's progress being made in that space as well.
So the millimeter continuum correlation was really interesting. But I guess dust also emits at millimeter wavelengths if you're in a star-forming galaxy. So is this really only going to work when you still have you still need that very high angular resolution to be able to isolate this source?
Yeah. So the brilliant thing with an interferometer is if you go high angular resolution, you resolve out all of the disk. And so you can actually get rid of all that dust emission very cleanly. And luckily, it doesn't take very long for these observations, right, in continuum. And so the hope is that one could do a snapshot program with a large array configuration of ALMA, even in the star-forming galaxies, to pick out those sources. Something I need to email Adam about to get the thanks data for this, see how it looks.
Maybe a similar question on your star formation relations, right? As I understand, you have derived the star formation rate from H alpha, but in principle, some of that escapes at higher wavelengths in the infrared. So, have you looked at adding the total IR to this correlation, and would it change? Because I mean, when we do that, I think in funds we see some fluctuations, and it is a combined measure that is a better and more well-defined measure of the star formation rate.
Yes, so it's something that we've looked at in the early type galaxies. Some of the unresolved Koenig-Schmidts I showed were with, for instance, the 24 micron and the PAR UV, combining those together. We see differences in the early type systems between the star formation rates you get in H alpha versus those you get in those traces. You have to be careful because old stars emit in also at, they have AGB dust shells, for instance, that impact you at 24 microns. And so you have to subtract those out, etc. But you get differences. So the H alpha in a lot of these sources, it doesn't look star forming if you do a BPT classification. And so you really are unsure about your star formation rates in those quenched systems. It can be very tricky. For KILOGAS, this is less of an issue. But the early type systems, measuring the star formation rate is hard.
I'm interested to learn a bit more about the diagram of the models of the accretion disks that you showed, where you have the disk, the cold disk, so to speak, going all the way to the last stable orbit, or a transition from a cold disk to ADAF. And this transition going from accretion in a cold mode to a hot mode has been, at least when I was like 25 years ago, I was doing some work on that. That was like the big mystery, why that happens. So I'm wondering, is this still one of those unsolved mysteries, or and do we know that there is a cold disk further out, or is this just an assumption that there is this cold disk? Because it could also be just the gas never managed to get into a cold phase and has always been hot.
Yeah, I think it's still quite unknown. I think there are individual sources where they think they see lines of a cold disk of larger radii, but I think it's still, these models of central engines are still very much a work in progress, and it seems like, you know, we have been getting multiple frequency coverage of some of our disks and trying to fit some of these models. None of them seem to work very well. So it seems like there's a lot still to be explored in that accretion mode at small scales that we don't understand.
So before we thank our speaker again, I'll just announce there are snacks and drinks in the room right next door. Students and postdocs, you are very, very, very much encouraged to come hang out, talk with the speaker a little bit more casually after the talk. And then there will be dinner at also for Zoom, Urban Kitchen 7. Feel free to sign up on the Google Docs stuff. Let's thank Tim.